Welcome to qnawire.
Hi, so in this question we're told that we have 3 moles of HI in a 5-liter vessel. So my initial concentration of HI is going to be equal to zero point 0.6 molar. And we're given that the equilibrium constant at 700 Kelvin is equal to 0.0183. So in this case, we want to know what percentage of the original HI would remain at equilibrium given the following decomposition for all of the gas phase species that we're going to get. So HI decomposes as H2 plus I2, all as gas. And the thing that we're going to do is we're going to start with our ice table over here. And we're going to employ the equilibrium constant in order to know what is going to be the equilibrium concentration of HI after the decomposition reaches that state. So initially we're going to have a concentration of zero point 0.6 molar of HI, 0 and 0 of the other gases. Then a portion equal to minus 2x, so 2x is going to be decomposed of HI, generating x and x. Remember that these amounts need to be corrected by the stoichiometric coefficient that we are going to put there. So at equilibrium, we're going to get zero point 0.6 minus 2x, x, and x. So our equilibrium constant for this reaction is going to be equal to, I'm going to write this down in scientific notation, is going to be equal to the concentration of H2 times the concentration of I2 divided by the concentration of HI squared. So, replacing the values that we get at equilibrium, this becomes x squared divided by 0 0.6 minus 2x squared. Now, in this case, the equilibrium constant does not have a very small value as we see in a lot of acid-base equilibriums, so we cannot do any approximations in order to solve for x. We need to solve the full quadratic expression. So the procedure is quite simple. We are going to expand this expression and get the result from the quadratic. So first step, we are going to pass all of this denominator to the left-hand side. So we have 1.83 times 10 to the minus 2 times 0 0.6 minus 2x squared is going to be equal to x squared. Expanding the left-hand side, we get 1.83 times 10 to the minus 2 times 0 0.6 squared, that is 0.36, minus the double product of the first term times the second. So this would be minus 2.4x plus the squared of the second term, so plus 4x squared. And this needs to be equal to x squared. We can simplify it a little bit further, simply replacing the equality with a minus, and this is going to be equal to 0. Simplifying a little bit the expression, we get minus 0.9268 x squared minus 0.04392x plus 0.006588 needs to be equal to 0. So now, solving the quadratic expression, we get two values. So x1 and x2. x1 turns out to be a negative value, that is 0.111272. But if we look at our ice table, the value for x cannot be negative because we cannot have negative concentrations. So we can discard that solution. The second solution that we get is equal to 0.0638827. And this is going to be our solution for x. Now, we want to know what is the concentration at equilibrium of HI. So remember that that was equal to 0 0.6 minus 2x. And the value for x that we're going to get is this value for x2, right? So 0 0.6 minus 2x gives us 0.4722346. Okay, And if we want to know the percent left, what we need to do is divide the concentration at equilibrium by my initial concentration and multiply the result by 100. Remember that this is the concentration at equilibrium. The initial concentration of HI was 0.6 molar. So the result for this is 78.7% is going to be left. And that will be all. Thank you very much.